Welcome to This Explainer. If you're sitting in this geology class, you probably think we've got Earth pretty much figured out, right? I mean, we live in the age of supercomputers and satellites, but today we're stepping out into the field to investigate some of our planet's most stubborn geographical mysteries. We're going to ditch the myths, look strictly at the raw observational data, and see exactly how current scientific consensus holds up against the unknown.
Think about it. Our planet has been mapped, studied, and photographed more intensely than at any other point in human history. We've got high-res satellites orbiting above us, remote research stations gathering data in the harshest environments imaginable, and AI crunching massive datasets. Literally, we have better, more comprehensive maps of the surface of Mars than we do of certain parts of our own oceans. Wild, right? Yet, despite all this incredible technology, we still have places right here on Earth that just totally challenge everything we think we know about the natural world.
Okay, here's our game plan for today. We'll start with an overview of Earth's unsolved geographical mysteries. Then look at the Bermuda Triangle hypotheses, the moving stones of Racetrack Playa, data collection in Romania's Hoia Baciu Forest, some remote ocean and desert anomalies, and finally, we'll wrap up by talking about the immense value of scientific curiosity.
So, jumping right into Section 1, Earth's Unsolved Geographical Mysteries. This is what I like to call the paradox of the modern age.
When you actually look at the raw data, this global pattern of anomalies starts to emerge. And look, we aren't talking about local ghost stories here. We're looking at documented baseline data. We're talking about compasses spinning completely out of control, pointing to massive localized magnetic anomalies deep beneath the crust. We've got unexplained vanishings of massive vessels, bizarre aerial lights that meteorology just can't easily explain, places where nature seemingly behaves in ways that break our standard physical models. These are the physical observable data points that drive geologists crazy, and honestly, they're exactly what drives our investigation today.
Moving on to Section 2, let's take that scientific lens and apply it to our first major case study, the Bermuda Triangle hypotheses.
Now, this heavily trafficked region in the Atlantic brilliantly illustrates the clash between sensationalism and actual scientific methodology. Popular culture loves to blame extraterrestrials or interdimensional portals for disappearing ships, but as scientists, what do? We look at the logical, physical evidence. The leading scientific hypotheses actually focus on massive underwater methane gas eruptions. Think of it like a giant glass of soda suddenly fizzing up from the ocean floor. These gas hydrates radically drop the water's density, completely destroying a ship's buoyancy and pulling it down in seconds. We're also looking closely at unusual localized magnetic fields there, where true north and magnetic north align perfectly, which can totally scramble standard navigation gear. It's about physical geology, guys, not the supernatural.
Okay, let's shift our geography for Section 3, the moving stones of Racetrack Playa. We're heading deep into Death Valley for this one.
So, picture this. You're standing on a completely flat, barren, dry lake bed, and there are these long trails carved right into the dirt by massive rocks. What's crucial here is the observational data. Some of these stones weigh hundreds of pounds. The physical tracks are right there, proving they traveled across the desert totally on their own, sometimes hundreds of feet, with absolutely zero human or animal help. For decades, this gave geologists a massive headache. Early guesses were weird seismic stuff or magnetic forces, but we really needed empirical, on-the-ground data to figure out this physical movement.
And the breakthrough finally happened when researchers captured the precise environmental data. Turns out it requires an incredibly rare, perfect storm of conditions. First, winter rain creates a shallow pond on the playa. Then, a rare overnight freeze creates this window-pane-thin sheet of ice. As the morning sun hits it, the ice breaks apart, and stiff desert winds act like sails against the jagged ice panels, literally shoving these massive, hundreds of pounds rocks across the slick, muddy surface underneath. It's geology in motion, and such a brilliant example of how rigorous observation of environmental factors can crack a case that seemed impossible.
All right, shifting to Section 4, Romania's Hoia Baciu Forest. Here we look at the challenges of data collection in a quote-unquote haunted environment. Visitors constantly report hearing unexplained voices, seeing weird lights, or suddenly feeling overwhelming anxiety. And on the tech side, consistent reports of electronics just dying or malfunctioning out of nowhere. But scientists tackle this strictly through the lens of unverified psychological or environmental factors. Could localized electromagnetism or low-frequency infrasound cause both your phone to die and your chest to tighten with dread? I mean, think about how weird you feel standing right under massive power lines. The huge challenge here is that human perception itself gets compromised, making objective data collection really, really tough.
Which perfectly brings us to Section 5, Remote Ocean and Desert Anomalies. This is all about confronting the strict limits of our observation.
To really put our limitations into perspective, more than 80% of Earth's oceans are still largely unexplored. Just let the magnitude of that number sink in for a second. It is a staggering geological reality that we currently know more about the dark side of the moon than parts of our own deep seafloor. Direct seafloor data collection needs submersibles that can survive crushing pressure. It's expensive, technically grueling, and massively restricts our research.
And this limitation directly impacts how we analyze underwater discoveries, like the 2011 Baltic Sea anomaly. A sonar team spots this massive, patterned circular structure deep on the seafloor, and boom, the popular claim instantly jumps to crashed UFO. But the leading geological theory? It's just an unusual, entirely natural glacial deposit or volcanic formation. Now compare this to Racetrack Playa. In Death Valley, we could literally set up time-lapse cameras on the dirt and observe the ice and wind. But with the Baltic Sea anomaly, we are stuck waiting for deeper, core-drilled geological data, because the extreme underwater environment just won't let us easily gather the proof.
And we see similar observational limits on land too. Take the Sahara Desert. Satellites have found these enormous, miles-long circular formations, like the Richat structure. Now, satellites are amazing pieces of tech for spotting structures from space. But a satellite can't pick up a rock. It can't test its chemical composition or do isotopic dating. Without boots on the ground and hands in the dirt, we can't definitively separate a natural geological freak occurrence from complex ancient engineering. Were they formed naturally by uplift and erosion, or something else entirely? Without direct physical data collection, the debate among scientists just rages on.
So, stepping back to look at the big picture, the scientific method is absolutely our best compass here. We've done a quick global tour of anomalies and the logical evidence driving our scientific focus. Whether we're testing methane bubbles in the Bermuda Triangle, physically tracking the perfect storm of ice and wind at Racetrack Playa, checking for infrasound in Hoia Baciu, or pushing for deep geological core samples in the Baltic Sea, this is how rigorous science logically categorizes the unknown so we can systematically decode it.
Let's wrap things up with Section 6, the value of scientific curiosity. Let's look at the philosophical takeaway of all these stubborn mysteries.
Think about the tools we have today. We've got orbiting satellites capturing high-res imagery, AI running complex geological analyses, LiDAR seeing through dense jungle canopies, and remote stations pulling physical data from Antarctic ice. Yet, even with all these incredibly powerful tools, we are still discovering new deep cave systems, extremophile species, and geographical anomalies every single year right here on Earth. The horizon of discovery isn't shrinking at all. It's constantly expanding.
And the core lesson here is vital for anyone studying geology or any scientific field. These stubborn, unsolved anomalies are not proof of extraterrestrials or the supernatural. They matter because they remind us that curiosity still matters. They are the essential fuel driving discovery forward. When we encounter something that defies our current understanding of physics or geology, it forces us to invent entirely new research tools. It forces us to refine our data collection, push our tech to the limits, and totally rethink the fundamental rules of the natural world.
So I want to leave you with this. How much do we really know about the world around us? And where is the next great mystery waiting to be uncovered? Every mapped anomaly proves that Earth holds secrets just beyond our current understanding. So keep questioning the data, keep analyzing the evidence, and keep exploring the rigorous science behind the unknown. Thanks for joining this explainer today. And remember, the more we map our planet, the more we realize just how much is left to discover.